y times y prime. And then we are also given that y of 0 is equal to 0. Okay, so we're actually given two pieces of information here. We're given the differential equation, and then we're also given an initial value. And so technically when you group these two together, this is called an initial value problem. And our goal is going to be to, first of all, find a general solution, which will have a plus c somewhere in it. And then once we figure that out, then we need to figure out what that c value should be to satisfy our initial condition. All right. Dennis, are you asking about this one because you'd like to see, or did you have a specific question about this one?
I just wanted to, like I said, I just wanted to see.
Okay, cool. All right, so here we've got this equation, and our goal is to first of all solve this differential equation. One option is the graphical method, where we solve the equation for y prime. We have y prime is equal to stuff. And then we could go ahead and graph it. But in this case, I think we can actually use separable equations and solve this analytically, which I think is really the route that we want to look at. Okay, so the very first thing that I would do here is I would say, okay, I've got x cosine x is equal to 2y plus e to the 3y, and I'm going to replace y prime with dy over dx. Now, when I look at this equation, it's not quite written in the form dy over dx equals g of y times f of x, but I can kind of see that I've got all my x's grouped together. I've got all of my y's grouped together. The only thing that isn't really grouped together is this dx I need to pull over to the left side, and that will separate my x's and my y's. So if I do that, then I've got x cosine x dx is equal to 2y plus e to the 3y dy. And now I've separated my differential equation. Are there any questions about that part? Okay, once I get to there, then I say, all right, great, now I'm going to integrate both sides. And so when I look at the left side over here, I have x times cosine x. What would be a good technique to use on this left-hand side? Yeah, by parts is a really good choice. I don't see anything that's kind of an inside function, so u sub isn't going to work, but I do see multiplication. And so I'm going to start by analyzing this left-hand side. The integral of x cosine x dx. And we'll look at by parts. So let's see, L-I-A-T-E. I've got algebra, and that comes before my trig, and so I'm going to let u be equal to x. And then my dv will be cosine x dx. So my du is equal to 1 times dx, and my v is going to be sine x.
Negative. Oh, no. Yeah, fine.
You're good? Yeah. Okay. Okay, so now we've got our u, our v, our du, and our dv. And so our integral is going to be equal to uv, so that's x times sine x, minus the integral of v sine x du, which is dx. And in terms of my integration technique, integration by parts, I want to stop here and take a look and ask myself, am I in better shape than I was with the original integral up here? And the answer is definitely yes. I've gotten rid of that x in the integral, and so now I know what the antiderivative of sine of x is. So I end up with x sine x minus negative cosine x, so I end up with a plus cosine x. Okay, so that is the left-hand side of my equation. I've got x sine x plus cosine x. Any questions about that part? Okay, so now I'm going to work on the right-hand side. I've got the integral of 2y plus e to the 3y dy. And so I see a plus sign in there, so I might start by separating this into two separate integrals. And so the first integral is easy. That one is going to be y squared. And my second one if I wasn't too happy about this 3y up here, then I could definitely do a u substitution. And so I'm going to quickly sketch out what my u sub will look like. My u will be 3y. My du over dy will be 3, which means that dy is equal to du over 3. And so I end up with the integral of e to the u times du over 3. And I can kind of think quickly ahead. I'm going to pull that 1/3 out in the front and take my antiderivative. So I've got y squared plus 1/3 e to the u. And then I can plug back in my u value. So I have y squared plus 1/3 e to the 3y. All right, any questions about that antiderivative right there? Okay, so that is the right-hand side of our equation. We've got y squared plus 1/3 e to the 3y. Now I'm being a little bit sloppy here, and there's a step here that I still need to include. Technically, both sides have a plus c, but the plus c's are different. I've got a plus c1 and a plus c2, and then I'm going to move them both to one side. It does not really matter which side I move them to. Typically, we end up putting that arbitrary constant on the x side, so I'm going to go with tradition and put the plus c over on the left-hand side of this equation. Okay. It does not matter because in the final answer, we're not saying what is c equal to, we're saying what is our final expression going to be. Okay. Any questions so far? At this point, we have a solution to our differential equation where y is implicitly defined. So this is a general solution where y is implicitly defined. If life was fabulous and awesome, then and we're really lucky all at the same time, then we'd be able to solve this equation for y. I don't see that happening in this particular example. So in this particular example, this is as far as we can go with the general solution. Our next step is going to be to use our initial condition. Any questions so far? Okay. Okay, so in order to use our initial condition says that when x is equal to 0, then y will also be equal to 0. So here's our x value, that's the one inside the parentheses, and the y value is the one on the right-hand side. And so we can plug 0 in for every x and every y and figure out what this c value should be for our specific initial condition. So we've got 0 times sine of 0 plus cosine of 0 plus c is equal to 0 squared plus 1/3 e to the 0. So we have 1 plus c on the left side, and on the right side we have 0 plus 1/3 times 1. And once I get to here, it's pretty easy to solve for c. I subtract 1 from both sides. So I have 1 plus c is equal to 1/3. Subtract 1, and I have c is equal to negative 2/3. And so our final answer, which is our particular solution, particular because we've now used our initial condition, our final answer is that we have x times sine x plus cosine x minus 2/3 is equal to y squared plus 1/3 e to the 3y.
Wouldn't it be plus 2/3, it's not negative 2/3. It's a positive 2/3 angle.
Well, when I subtract my 1 from both sides, I ended up with c is
okay.
equal to negative 2/3. So I could do plus and negative 2/3, but it would still be. Now, if you chose to put your plus c on the right-hand side over here, then your c value that you would have come up with would have been a positive 2/3. And then over here you'd have all this without the minus 2/3,
That's what I did.
plus 2/3 on the
That's
right
what I
side.
But that's right, go 2.
And what?
That's right, go 2.
That would be absolutely fine as well.
Okay.
I mean, whether your equation where you have plus 2/3 on this side rather than minus on the left is an equivalent equation. Matt, you have a question?
Actually, didn't figure it out.
You got it? Okay, great. Okay, other questions about this particular example, number 11? Integral from 0 to 1 of e to the minus x squared dx. And we looked at the graph of this function, e to the minus x squared dx. And it looks something like this, which was the shape of, roughly the shape of the bell curve. And we were interested in the area starting at 0 and ending at 1. Now, fundamental theorem of calculus says, hey, if we want to calculate this area, what we need to do is find our antiderivative. This is a continuous function, so, and these are numeric boundaries. Our function is continuous between the values of 0 and 1. So fundamental theorem applies. All we need to do is find the antiderivative of e to the minus x squared, plug in the boundaries, and we're done. But the problem is that this function does not have a nice elementary antiderivative. So any of the tools that we spent the first month and a half of class on learning, not going to work here. Okay, this guy, there's nothing we can do here. And so there's a lot of integrals like this. And the thing is that because we cannot find a nice antiderivative, we're going to have to approximate this area. So since e to the minus x squared does not have an elementary antiderivative. That word elementary is really frustrating, right? Because, I mean, we are in Calc 2, and the word elementary typically refers to 1st through 6th grade. And so that's not what they mean here. What they mean here is that there's no nice closed form where you've got this function that you can write down between my two hands, and then if you take its derivative, you get e to the minus x squared. One just doesn't exist. There is, and we'll talk about later in the semester, there is a way that you can write this that is an infinite sum of terms, but that's not elementary because it goes on forever and ever and ever. And so that's fine, but that's not going to work for us here. Okay, so since e to the minus x squared does not have an elementary antiderivative, we must use approximation techniques to evaluate the integral from 0 to 1 of e to the minus x squared dx. Now, if you're working in engineering, you're going to come across tons of functions that don't have nice antiderivatives. Or you may even have curves where you don't even have a formula for the curve. All you have is a bunch of data points along that curve, and you have not even approximated a curve to fit your data. You just have those data points. And so in this case, our approximation techniques here are the beginning step in terms of how you find the areas under those curves when you're not given an actual function or when you're given a function that doesn't have a nice antiderivative. Okay, so last class, I think it was Matt who said, well, isn't this kind of like a bunch of Riemann sums? And the answer is yes. So I want to remind you about something you talked about at the very end of Calc 1. You talked about approximating area under curves using rectangles. And in particular, you might have talked about using right-hand rectangles, and you might have talked about using left-hand rectangles. And so what I'd like to do is to do an example that reminds you a little bit about the end of Calc 1. All right, so we are going to choose our number of rectangles to be 5 so that this is a reasonable thing to do with a hand calculator. So we're going to use 5 subintervals. And again, we are only interested in the area under this function under y equals, or f of x equals e to the minus x squared. We're only interested in the area between x equals 0 and x equals 1. And so if I want to use 5 subintervals, and I want to use right-hand cornered rectangles, the first thing I'll do is split this interval from 0 to 1 up into 5 equal units. And so that means 1, 2, 3, 4, 5. So I've drawn them in here, and so now the width of each of these is going to be a distance of 0.2. And so I can get that by, if I want to, I can do a calculation. Delta x is b minus a over n, where 1 is my b, 0 is my a, and n is 5. Or I can look at this and say, look, the distance is 1, and I need to divide that up into 5 equal units. But 1 divided by 5 is 0.2. So I can mark off these other values. So we have 0.2, 0.4, 0.6, and 0.8. All right, so my right-hand rectangles say that in my first interval, I use the right-hand corner of that rectangle to determine the height of the rectangle. So the right-hand corner touches my function. And I do that all the way across here. And so I'm going to be using these 5 rectangles here to approximate the area under our function e to the minus x squared. Now, symbolically, if I want to think about these values symbolically, I'm finding the area of my first rectangle plus the area of the second plus the area of the third plus the area of the fourth plus the area of the fifth. I'm going to go ahead and label these. My left-hand mark that I have here is x0. My 0.2 will be x1. My 0.4 will be x2. 0.6 will be x3. 0.8 will be x4. And my last one will be x5. And so if I want to approximate the integral from 0 to 1 of e to the minus x squared dx, this is approximately equal to the height of my first rectangle, which is f of 0.2, or f of x1, times the width of that rectangle, which is delta x. And then I'm going to add that onto my second rectangle, so I have f of x2 times delta x. And I have 3 more of these to do. My third rectangle, the height of the rectangle depends on x3. So the height is f of x3 times delta x plus f of x4 times delta x. And I need a total of 5 of these, so my last one is f of f5, f of x5 times delta x. All right. Are there any questions? I wrote that all symbolically. We haven't done any calculations yet. Any questions about those symbols? So does this look semi-familiar from the end of Calc 1? Hopefully a little bit. Okay, great. All right, so now we've got to have some computations here. So what I'm recommending is that we end up making a table. You can set up your computations any way you want. I'm going to set up a table so that I have 2 columns, where my first column is the xi's, and so I'm going to have x1, which is 0.2, x2, which is 0.4, x3, which is 0.6, x4, which is 0.8, and x5, which is 1. And then I'll have a second column, which has the y value that is associated to each of those. So we have f of 0.2, we need to calculate f of 0.4, f of 0.6, f of 0.8, and f of 1. All right. Now our function that we're looking at is e to the minus x squared. So I'm going to be, everywhere that I see an x, I'm going to replace that with a 0.2. And I'm going to replace that with a 0.4. And so what I'd like you to do right now is I'd like you to turn to one of your neighbors and say, hey, you're going to be my partner here and we're going to figure these out. And then I want you to split up the work and calculate all 5 of these y values. Should really be pulled out. And so up here, we've got, this is really delta x times the sum of all of these. And so please add up all these numbers and see what you get.
Oh, no.
Somebody's got to.
Equal 404.
I got 3.404. Oh, that's
Ben, what did you say first?
3405.
3.405, 3.404,
3.44.
44,
404.
44.
I was just going to say, I got some.
Oh, were they, because of this negative up here?
Yeah, because I got for my, like for my F8, I got 1.9.
Are you using
I
X
got
or
the
E?
same thing.
Put it in my calculator.
E to the power of -8. Power of 2, right?
So one thing you want to be careful of here is that when you are typing in, let me draw this over here. When you're typing this into your calculator, make sure that you have parentheses around the negative x squared, so that the negative and the x squared are all in the power. And then also make sure that you do not have parentheses around the x with the negative, because you only want to square the x, you do not want to square the negative. But you do want the whole thing to the power.
I didn't
That
put
work out
parentheses
better?
in. Mine came out good.
Okay.
Depends on your calculator.
Okay, so 3.405 or 3.404. Look at that.
It rounded up.
Okay, so it rounds up to 05 or 04. That's not really crucial here. Okay, so this is our sum. So we have delta x times 3.405. Our delta x, that is the width of each rectangle, and the width is 0.2. So we have 0.2 times 3.405. What do you get when you multiply those out? 6.810.
0.681.
Oh, yeah, thank you. 0.68. 0.6810. All right, so we have just used the right-hand rule to approximate the area under our function e to the minus x squared. Okay, any questions on running that calculation? Okay, so when you look at that, there's a couple things that the function is horizontal rather than being curved the way it is. So we are using constant functions to approximate our curve. We're using right-hand corners. We could also do the option of using a left-hand corner, or we could even use the middle of the interval and do a midpoint rule. Okay, so these are all different options. Let's compare this to what you might get on your calculator. Is that we want to use n subintervals to approximate the integral from a to b of f of x dx. And so we call that calculation Rn. Okay, R for right-hand rule, N for the number of subintervals. And so the way that we worked it on this particular problem, we labeled our x values across the bottom, and we calculated f of x1 times delta x plus f of x2 times delta x plus dot dot dot, and we went up to f of xn times delta x. And so these were the symbols that we used, and we can rewrite this a little bit. We can factor out the delta x, and we've got delta x times the quantity f of x1 plus f of x2 plus dot 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 plus f of xn. And way back with the Riemann sums, you might remember that we took these really long sums and we crushed them down into summation notation. And so we might write this as delta x times the sum of the f of xi's, where I goes from 1, then goes to 2, then to 3, all the way up to n. And so this is technically the right-hand rule for approximating a definite integral. Now, there are some things in here that we need some values for. For example, delta x. Delta x is always b minus a over n, so the two endpoints subtracted, divided by the number of intervals. And the xi's, so think about this. The xi's start at our right-hand value, the a, and then add on some number of delta x's. And how many you add on? Well, you add on I of them. Okay, so those are the x values. Now, do you actually need this value to write down what the labels are? No, you don't. This is the technical equation that will give you those values, but you can figure out those values without this formula as well. Okay, so let's see if this thing's going to work now.
It's not on.
All right, and you'll notice a whole bunch of things on there. You can scroll down until you get to number 9, which is fn int. So math 9 will be fn int. And so once you get to that, then the next thing you want to do is you want to type in the name of your function, which in this case is e raised to the negative x squared. So you hit enter on the fn int, and then you type in e raised to the negative x squared, and then you want to put a comma in. Okay, and so there's a comma right below the sign function on your calculator. And you're going to integrate with respect to x. So that's the next thing that goes into your calculator.
0.746.
After that, we want to integrate from 0 to 1. So we'll put those boundaries in next and then close parentheses. Oh.
Mine looks like that.
So that...
0 to 1 in this thing.
It's because there's a software update.
So if you have a software update in your calculator and it comes up looking like the integral with the little boxes,
Yeah,
and the little
mine
functions, and the d in the box here, then fill in the stuff the way that it would make sense to fill it in. Okay?
The problem with that is the answer is the integral itself.
On the TI-83 it may not be. On the TI-89 it will be.
What about the
And you
TI-84?
have the Inspired?
Same thing with 80.
Okay, so if you have an 83, then your calculator is set up to do the numeric approximations. And when you type this in, you should get a value. Did anybody hit enter?
Yeah. 0.746.
So 0.746. Do I have a second on that number?
Second.
Great. Okay. So if you have a TI-83 or TI-84, then this should be the final value that you get, whether you use the software update down below here, or whether you use the standard notation that comes packaged with your calculator. You should end up with this 0.746. Now that totally makes sense in terms of that number is larger than the number that we came up with. And if you look at your picture on your paper, you'll notice that the rectangles don't take up all of the area. So it makes sense that the actual value is a little bit larger. For those of you that have a TI-89 or a TI-Inspire, when you type in your integral of e to the minus x squared dx from 0 to 1, the output that you get is the integral from 0 to 1 of e to the minus x squared dx. And that is unsatisfying because it doesn't actually give you a numeric value. And the reason for that is because this antiderivative here, your TI-89 and your TI-Inspires are actually finding the antiderivative using the fundamental theorem, plugging in the boundaries, and then subtracting. And because this guy does not have an antiderivative, your calculator does not know what to do with it. So for those of you with a TI-89 or a TI-Inspire, you've got to find the button that says, give me a numeric approximation. And once you do that, then you should get a value that's 0.74.
All you gotta do is hit Control Enter.
Control Enter?
Yeah.
Great. Okay, Control Enter is your numeric button.
You can also, if you plug the equation into your y equals, you can do second calc.
Yes.
And do it like graphically.
So that's a really cool way to do it as well. So the other option is, besides doing this with this calculation here with the Math 9 button, the other option is to graph y equals e to the minus x squared. Make sure that your graph is graphing, looking at least between 0 and 1, and then do second calculate, and go down to number 7. And it'll ask you for a lower bound and an upper bound, and it will give you the same, should give you the same approximation. Okay, so we've got the right-hand rule. There's also a left-hand rule and a midpoint rule, and I'll leave those for you to look at in your textbook. You've kind of looked at that before in terms of Calc 1. What we're going to talk about after the break here is what happens if we approximate using something better than a constant function. Okay? And so we will look at an example where we're going to look at using linear functions to approximate our curve. So what happens when we make an approximation that is better than a constant function? In other words, what if we make the top of our rectangle something more interesting than just a horizontal line? All right, so we'll look at that after the break. Please take a 10-minute break, and when you come back, we're going to talk about the trapezoidal rule. Welcome back. So here's our new idea. So the new thing that we're going to be talking about is, rather than approximating using constant functions, we are going to approximate our curve with line segments. Now, our other ones were also line segments, but they were constant functions or horizontal line segments. So we want to approximate our curve with line segments and add the areas of the corresponding shapes. Okay, so if I have, with our example, where we have the integral from 0 to 1 of e to the minus x squared dx, here's our function, starting at 0 and ending at 1, and let's say that I again broke this up into 5 subintervals. Rather than looking at taking the right-hand side of my rectangle and drawing a horizontal line across, what I'm going to do is take the 2 endpoints on both sides of this interval and connect them with a straight line. Now some of these, the straight line almost looks like it's exactly the same as the curve itself. Not every time, but many of these times. It seems like our approximation is going to be much better. And so we are approximating our curve with a bunch of linear functions. And so these blocks of space that we have that we need to find the area of, those are all trapezoids. And so this is called the trapezoidal rule. Alright, so just like the right-hand rule, we can write down a nice formula for the trapezoidal rule, and here's how it works. So here is the derivation of the trapezoidal rule formula. Now again, this is not going to be on exam 2, but it is fair game for exam 3, and this is a really good question to be able to explain to your dog, or to your housemate, or to your parent, or your child, or whoever is willing to listen to you, so that you can explain where the trapezoidal rule comes from. Okay? AKA, be able to explain this for a test question. Okay? Exam 3. Okay, so here's how this works. So we've got this generic function. Here it is. There it is. There's our function y equals f of x. And we are interested in approximating the area under y equals f of x between a and b. Now, if our function happens to dip below the x-axis, then we have negative values, and that's fine. Just in terms of picture, I'm just going to go ahead and use positive values here. And so we want to approximate the integral from a to b of f of x dx using n trapezoids. So the first thing I do is I'm going to break this up into n subintervals. And our left-hand side over here, the a value, we call that x0. And then the next mark over will be x1. The next mark over will be x2. And then we'll go x3 and then dot, dot, dot. And the very last one will be xn. Now in this specific example, our n value happens to be equal to 5, but in general it will be the nth marking. Okay, so from there, I'm going to go ahead and draw my trapezoids. And so I can create my trapezoids by connecting the two endpoints of the subinterval. And there it is. Okay, so at this point, I need to know the area of a trapezoid. So I know what the area of a rectangle is. That's easy. It's base times height. But you might want to recall that the area of a trapezoid is, well, if I have a trapezoid that is shaped similar to the types that we have in our picture, I've got two separate lengths, a length 1 and a length 2. And then I have a width, which is the length across the bottom. And so the area of this trapezoid, the way we get the area is that we average the two lengths. and then multiply that by the width. And so our area is 1/2 times L1 plus L2 times W. Okay, so here is our formula. Tn is going to be equal to, well, we have to add up all the areas of all these trapezoids that we have here. So our first trapezoid has an area that is going to be 1/2 times, okay, what happens next when we need the length on the left side and the length on the right side? So for our first trapezoid here, that means f of x0 and f of x1. Okay, so that's our length 1 and our length 2. And then our width, the width of our trapezoid, how can we describe that? Yeah, that would, if we were making these infinitely narrow, then that would be dx. But since we're not making them infinitely narrow, we'll call it delta x. All right, so a nice thing that we can write in here is that the width of one of these subintervals is delta x. Okay, so that's the area of our first trapezoid. Any questions about that one? Okay, so then we've got our second trapezoid, which is 1/2 times, okay, so now we're working on the second trapezoid. The left-hand side height is f of x1, the right-hand side is f of x2. So 1/2 times f of x1 plus f of x2 times delta x. Plus, we'll go on to our next one. We have 1/2 times, okay, the next rectangle over, we have f of x2 plus f of x3 times delta x plus dot, dot, dot. And so we have a whole bunch of these trapezoids here in the middle. And then let's go over to our very last trapezoid over here. Our last trapezoid will have area that is 1/2 times all right, this left-hand side over here. What's our subscript on this x?
N
minus 1?
Yeah, this is going to be n minus 1. It's one less than our last x value. So we're going to be looking at f of x of n minus 1 plus f of xn times delta x. All right, so this is our Tn formula. And there's an awful lot of stuff going on in here. So we want to clean this up a little bit. So take a look at what happens. What do you notice that's in common on every single one of these terms?
1/2.
Yeah, there's two things going on. And I heard a couple people say the 1/2 and some people say the delta x. Let's pull both of those out. So we've got 1/2 times delta x. And then so what we're left over with here is we have f of x0 plus f of x1 plus f of x1 plus f of x2 plus f of x2 plus f of x3 plus dot, dot, dot plus f of x n minus 1 plus f of xn. All right, so on each of these terms, I have pulled out the 1/2 and the delta x, and then I've grouped the rest of the pieces together. All right, anybody see anything else that we could clean up here?
There's several repeated terms, so like the x2, there's 2 of those, and 3, there's 2 of those. And
all of them except 0
And then,
and
yeah, even though I don't see another f of x3 term, that's part of the dot 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 part. That would be our next one. And we don't see a second f x minus 1, but its pair is inside these dots as well. And so that's a really good observation. We have 2 of everything except for the x zeros and the x n's. And so we can write this as 1/2 times delta x times f of x0 plus 2 fx1 plus 2 times f of x2 plus dot 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 plus 2 times f of xn minus 1 plus 1 times f of xn. And so in the end, we can write our trapezoid formula Tn is equal to 1/2 delta x times f of x0 plus twice f of x1 through f of xn minus 1, and then 1 of the last one. So this is our formula where delta x is equal to b minus a over n.
So it's just 2 times every number except the first and the last.
That's right, 2 times every number except for the first and the last. And so your job is to be able to show where the heck all these extra 2's come from. In other words, say, okay, here is the formula for our trapezoids. Let's write these all out, regroup the letters until we get down to this bottom line down here.
If
Any
we
questions? Oh, sorry. Go ahead.
If we did it just like that, though, it'd be okay.
And it would be totally just fine, just
No,
like
I mean,
this.
above that,
Oh, this line here?
or do you want us to group the,
So the way the test question would be formed is, I would say, the trapezoidal rule is this. Show us how we get there.
but I mean, would you want us to group f of x2 plus f of x2 together to show that then
Oh, you
we
mean
would go
with
to...
parentheses?
Yeah.
No, I mean,
Okay.
as long as you have all of these guys written out,
Okay.
and then you can look at it and say, look, there's 2 of them. That's fine.
You said exam 3, do you mean the exam after this or the exam coming up next?
For the trapezoid rule?
Yeah.
This will be on exam 3. So the material about numerical approximations is not on exam 2.
Okay.
I don't like to do new material the day right before the exam.
Gotcha.
Okay, other questions? Okay, so this is our trapezoidal rule. Let's do one example here. So let's take a look at the integral from 1 to 2 of 1 over x cubed dx. Now, you can check by hand. So remember, the purpose of doing numeric approximations is to deal with integrals where you can't find a nice antiderivative. But this example is one where we do have a nice antiderivative. We can do this by hand. And the reason is I want to be able to compare our actual answer with the approximate answer we're going to get with the trapezoid rule. So if you check this by hand, then the integral from 1 to 2 of 1 over x cubed dx is equal to 3/8. Find your antiderivative, plug in the boundaries, and 3/8 is 0.375. Okay, so that is the actual value of this integral. Our job is to find T4, which means by writing down find T4, it says we're going to use the trapezoid rule to approximate this integral, and we're going to use 4 subintervals to do so. Okay, so what I might start to do, and there's no reason that you absolutely have to do this, but I like to have pictures. So here's a picture of f of x is equal to 1 over x cubed. We are interested in the interval from 1 to 2. And we'd like to break this up into 4 subintervals, so n is equal to 4. So that means that here are our 4 subintervals. in terms of the symbols that we have for our formula over here, 1 is our A value, which is x0. 2 is our B value, which is xn, which in this case, n is equal to 4. Now, in terms of the middle portion here, I know that delta x is going to be taking my two endpoints and finding their difference, and then dividing by 4. So delta x is b minus a over n, which in our case is 2 minus 1 over 4, which is 0.25. So I can label my other values as well. I can look at 1.25, which is my x1 value, 1.5, which will be my x2 value, and 1.75, which will be my x3 value. So I want to be able to label all of those, and then I can draw my trapezoids on here. Here they are, all drawn on. And on this curve, it looks like they're going to be a pretty good approximation to our actual curve. Okay, so in our example, we have n is equal to 4. We've got our formula over here, so T4 is going to be 1/2 times delta x times f of x0 plus twice f of x1 plus twice f of x2 plus twice f of x3, and then we have 1 of the f of x4s. And so we've got to fill in all of this information. Things that we can fill in right away, the delta x is equal to 0.25. And I might make up a table for myself for the other values. I need each of my xi's, so I know I need x0, which is 1, x1, which is 1.25, x2, which is 1.5, x3 is 1.75, and x4 is 2, and I need function values for each of these x values. So we need f of 1, f of 1.25, f of 1.5, f of 1.75, and f of 2. All right, so please calculate some of these values. You can split them up with your neighbor if you like, or you can do all 5 of them on your own. When you get some values, check with your neighbor and see if they agree. So even if you don't have all 5 of those values, compare the ones you have with your neighbor, see if they agree.
Yeah.
At least
Jeff, do you and your neighbor agree?
Mm-hmm.
Did we tell me what numbers you came up with in school?
1.512, 0.296, 0.186, 58 as well, 0.125.
Okay, do I have a second on this list of values?
Could be
Great.
0.87.
Okay. All right, so these are our y values. Now in terms of our formulas up here, we're going to have to double these three middle numbers. And so in the end, what we're looking at is T4 is equal to 1/2 times 0.25 times 1 plus 2 times 0.512 plus 2 times 0.296 plus 2 times 0.186, and we're not going to double the last number, so we have plus 0.125. All right, so this is our T4 value. Has anybody gone ahead and crunched all this out?
Yeah, it's 0.4047.
0.389.
That's
That's what I got, 0.389.
Okay, I see a couple of people saying 0.389.
The exact number is 0.489 and 0.404 is, I mean, you got what you got, so yeah, I'm not gonna stand here and stubbornly defend my numbers, but just round the error.
I got
What was your number,
0.389.
0.389. Mark, what was your number? Just real quick.
Just a second.
Okay, I'm holding on. Okay, well, do I have a second for the 0.389? Okay, so we're going to go with that one for now. So this is our T4 value. All right, so we've used the trapezoid rule to approximate the area under this curve starting at 1 and ending at 2. Are there any questions on coming up with that value? Certainly there will be some rounding differences if you choose to keep more or less decimal places on these numbers. Keeping 3, I think, is a pretty reasonable value, or a reasonable number of decimals. Okay, so this is our T4 value. All right, now once we have this 0.389 or whatever we end up with, then we can compare that to our actual value. And so the big question is, how far off are we from our actual value? So we want to talk about a magnitude of error. And so the magnitude of error is the absolute value of the difference between our trapezoid value and the actual value of the integral. And so the way that we write this, we call this the magnitude of error, E for error, of the trapezoid rule. And so the way we can calculate this is, well, we just take our actual integral from 1 to 2 of 1 over x cubed dx, and we subtract off the value that we got when we approximated the integral. So in our case, that means that we're looking at 0.375 minus 0.389. And so the difference between the actual integral and the value that we got on our trapezoid rule is going to be 0.014. And so this is our magnitude of error. And so that's pretty easy to calculate if you know two things. If you can calculate the integral and you can calculate the trapezoid rule, then you can subtract the two and say, look how close they are. Our approximation is off by 0.014. Now, that's fine, but it's really kind of a stupid comment, right? Remember, the entire goal of these integral approximations is, how do we approximate integrals when we are unable to write down the actual value of the integral? And in that case, when we don't have an actual value for the integral, when all we have is an approximation, how do we figure out how close we are to the actual integral value? And so these are two big questions that we have. Number one is, how do we know how close our approximation is. How do we know how close our approximation is to the actual value of the integral from a to b of f of x dx? So how do we know how close we actually are, in particular when we don't know what our actual definite integral value is? That's one question. The second question is, when you go out into the engineering lab and you want to use this trapezoidal rule as an approximating technique, and you say, I need for my answer to be within 1/100th of the actual value, how many of these rectangles or subintervals do I actually need to make that happen? Do I need 4? Do I need 400? Okay. So another question here is, how many subintervals do we need to make our approximation fall within an allowable error tolerance? And so these are the two big questions that need to be asked and eventually need to be answered. We're not going to do these today, but we're not quite done with this section, but these two questions are basically the crux of when is this technique useful and how much work do I need to put into this technique to actually get an answer that I'm happy with.
Depends on what you're trying to do.
Yes, so the answer of what is the allowable tolerance comes from depends on what you're trying to do. So once you figure out what you're trying to do and what the allowable tolerance is, then we ask, okay, how many subintervals will I need? And it turns out that we're going to be able to answer that question using an error tolerance formula, which we'll talk about after the spring break. All right, questions or comments on this? Okay, so I'll give you some practice problems, but again, I do not want you to focus on these practice problems.